Dear student, in this video, I am going to share with you fused ring systems. In fused ring system, we have to discuss 6-6 fusion, that is Decalin system, then 6-6-6 fusion. Under this fusion, we have to discuss two molecules per hydrophenanthine and per hydroanthacene. Then 6-6-6-5 fusion. This fusion is observed in steroidal system. The next one is 6-5 fusion, that is hydrogen dense system. And the fifth point is small fused rings. In this video, I'm going to share with you 6-6 fusion, that is Decalin system. So, in this 6-6 fusion, the points I'm going to cover with you: the introduction, nomenclature, the synthesis of Decalin, the conformations, the stereostructure, ring flipping, energy calculations, and optical activity. So let us start with the introduction. Now, as we talk about the fused ring system, so the fused ring means what? Now look at here, this molecule is called as a fused bicyclic, while this structure is breached bicyclic molecule. Okay, you can see the difference here. The two atoms which are common in between these two rings. So these two atoms are common in between these two rings. And again, one more feature you can see, these two atoms are adjacent atoms. So the definition of the fused ring system is when the two rings fused with each other, then the adjacent carbon atoms shares between these two rings. That is, the two rings are fused by adjacent carbon atoms with each other. But you can see here in the breached bicyclic system, these two carbon atoms are called the breach-head carbons, from where we can start the next ring. That two carbons are called as a breach-head carbon. Same, this also called as a fused carbon. Now here, this breach-head carbon atoms, there is one more carbon atom in between them. Not necessarily only one carbon atom, you may have a different number of carbon atoms over here. So these breach carbon atoms are non-adjacent carbon atom. So again, this is there are two cycles. It is again a bicyclic compound, and in the bicyclic compound, the two atoms are common among these two rings, which are not adjacent carbon atoms. So that type of systems are called as a breach system. So you can see here, fused ring share two adjacent carbon atoms, while breach ring share two non-adjacent carbon atoms with one or more carbon atoms between them. So here you may have one or two or more than that carbon atoms between them. So in this chapter, we are going to talk about the fused bicyclic system. Now the nomenclature, how to name this system. Now this is a fused system. The reason behind is these two atoms are adjacent, which are common in between these two rings. Now the stereochemistry at the fused carbon. So these are the fused carbon. The stereochemistry at the fused carbon, one hydrogen is in the top direction going up, while the another hydrogen at the fused carbon is going in the downward direction. So the stereochemistry of these two hydrogens is opposite at the fused carbon. Therefore, this system is called as a trans system. If the stereochemistry of the two hydrogen atoms at the fused carbon atoms is opposite, then this is called as a trans geometry. Now, how to name this? So this is the naming pattern. How to name the molecule. As there are two cycles, so the first is bicyclo. After that, you have to write down the square bracket. In the square bracket, this is the common bond between these two rings. So on the basis of this common bond, look at here, on the left side of this, the carbon atom which are free, that is number 1, number 2, number 3, number 4. So that is the first number. How many carbon atoms are present on the left side of the common bond? So with respect to that, first that number we have to write down over here. On the other hand, that is on the right hand side, again 1, 2, 3, 4 carbon atoms are there. Therefore, again we have to write down 4 by placing a comma after the first 4 number. So the 0 indicate what? The 0 indicate there is no carbon atom in between the fused carbons. So these are the fused carbons and there is no carbon atom in between them. So that indicate it's a 0. So for fused system, the third place is always a 0. But for bridge system, the third place can be 1, 2 or so on. Now the total number of carbon atoms, there is 4 this side, 4 this side and 2 are over here. So total 10 carbons are there. 10 carbon means it is a decane. So the naming of this bicyclo 440 decane. So this 4 stands for number of carbon atom present on the left side of the fused atoms. The second 4 stand for the number of carbon atoms which are present on the right side of the fused atoms. And the 0 stands for the number of carbon atoms in between the fused atoms. So, as there is no carbon atom in between the two fused carbon atoms, so that number is 0. So overall, there are 10 number of carbon atoms, so it is called as a bicyclo 440 decane. And the stereochemistry, the common name of this is Decalin system. The stereochemistry at the fused carbon atom is trans, so the commonly it is called as a trans decalin. The same compound here, but only the difference is the two hydrogens are cis to each other at the fused carbon atom. Therefore, this is called as a cis decalin system. Now, this is the next, that is 6-membered ring fused with 5-membered ring. So, total number of carbon atoms are 9. Therefore, it is no name. Again, two rings are there, therefore it is bicyclo. This is the common atom that in between the two rings, or we call it these are the fused atoms. So on one side of the fused atom, there are 4 carbon atoms, so it is 4. On the other hand, 3 carbon atoms, so 3. And in between the fused atom, no carbon atom. Therefore, that's a 0. So it is bicyclo 430 no name. Now in this case, this is a 5-5 fusion. So 5-5 fusion, total number of carbons are 8. Therefore, it's an octane. On one side, it's a 3 carbon. On the other side, again 3 carbon. In between the fused carbon, no carbon atom. Therefore, it is bicyclo 330 octane. So this is the way to give the naming to the fused system. Now, how to synthesize this cis decalin and trans decalin? So that is synthesized from the naphthalene. So it is treated with the 2 molecules of hydrogen, that is a reduction reaction. So these 2 double bonds are undergoing reduction. So we call this molecule as 2 double bonds are reduced, therefore it is tetraline. Then again these 3 double bonds get reduced, so you need a 3 molecules of hydrogen. So this undergo reduction, this benzene ring undergo reduction, therefore it gives the stereochemistry at the fusion point, either cis or trans. So with respect to that, if the stereochemistry is different, it is termed as trans decalin, and this one is cis decalin. Now the conformations. So just now we discussed the trans-decalin bicyclo-440 decane, cis-decalin bicyclo-440 decane. So there are two conformations possible for this decalin system, that is trans-decalin and cis-decalin. First of all, you name the ring, first ring as A, the second ring as B. The numbering in this case start from this carbon, then continuous numbering up to 4, then the number at the fused carbon is given at the A. So number 4, 5, 6, 7, 8, 9 and 10. So this is the pattern of numbering in decalin system. Same here, the fused carbons are numbered at the end and the continuous numbering is there 4, 5, 6, 7, 8, 9, 10. Well, the stereochemistry of these two protons is cis, that is they are facing in the same direction. Now the stereo structure for this. Trans-decalin. So what you do, you first draw the ring B. After drawing the ring B, next you place the number 9 carbon and number 10 carbon on the left hand side. The reason is, you can see here number 9 and 10 carbons are on the left hand side of the ring B. So first your duty is to draw the ring B in a chair conformer. So draw the ring B in a chair conformer. Then you write down the numbers, number 9 and number 10 on the left side of the ring B. And after that, depending upon the stereochemistry, look at the stereochemistry. At number 9, hydrogen is beta. At number 10, hydrogen is alpha. So with respect to that, the stereochemistry, you can see here, number 9, hydrogen is beta. That means facing in upward direction. That's why this bond is axial. This hydrogen is axial as it is facing in upward direction. So, of course, this hydrogen is again facing in a downward direction. So, again, this bond is axial. So, these are the ring bonds which remain. These ring bonds are equatorial and equatorial. So, draw these two bonds and complete a 6-membered ring. So, that is ring A. And then you complete the numbering, that is 1, 2, 3, 4. And you label the fused carbon at the end. So in trans-decalin system, the one hydrogen is up, while the another hydrogen is down. The shape of this system is linear shape, that is trans-decalin is having a linear shape. Now in case of a cis-decalin system, the same thing, first you draw the ring B. So you can see the way we draw the ring B here, but only the change is, you can see in the cis-decalin system, the stereochemistry differ at number 10 carbon where the hydrogen is again a beta. So number 10 carbon, the stereochemistry is different. So with respect to that, initially the number 10 hydrogen is axial. Now number 10 hydrogen is equatorial. So only that is the change. This now hydrogen is equatorial and this hydrogen is axial. So it is what? The ring bond remain here is, this bond is equatorial ring bond, and at number 10 again this bond is axial. So then use this equatorial and axial bond to complete the ring A. So complete the ring A. Now in this case, both hydrogens are up, facing in the top direction. So you can see the stereochemistry of both the hydrogen is beta. So the stereochemistry of these two hydrogens is beta. Beta means facing in up. While this hydrogen in the trans-decalin, this hydrogen is beta, while the another hydrogen is alpha. So this hydrogen is alpha, that is facing in a downward direction. The stereochemistry of this cis-decalin system is that both hydrogens are facing in upward direction. Therefore, one ring, that is ring B, is in horizontal direction, while the ring A is vertical. The shape of this cis-decalin system, you can see this shape is a concave shape. So the shape of cis-decalin system is called as a that is the concave shape. One more thing, that is in case of a cis-decalin system, this, that is the lower part, we call it is the alpha side, is more hindered. The reason behind it, this axial hydrogen present at fourth position and this hydrogen which is the axial present at sixth position. Because of this, there is a less vacancy for the attack of reagent, and that's why we call this lower side, that is alpha side, is little bit hindered. So the in case of cis-decalin system, the top side is less hindered as compared to the bottom side. So top side is less hindered. Now in this slide, you can see how the cis-decalin system and trans-decalin system in a three-dimensional, how these molecules look like in three-dimensional structure. So in this structure, you can see both these two hydrogens at the ring junction. These two hydrogens are anti to each other. That is, these two hydrogens are, one hydrogen is up, another hydrogen is down. And you can see here in cis-decalin system, you can see both these hydrogens are in the same direction, both are facing in the same direction. One hydrogen is axial and another hydrogen is equatorial. Now the ring flipping. Trans-decalin not undergoing a ring flipping. The reason behind it, now you can see ring B flips. After flipping of the ring B, you can see that number 7 carbon is going in a downward direction, while number 10 carbon going in a upper direction. So this is the flip structure of ring B. So because of this flipping, now the C9 hydrogen, that C9 hydrogen initially it is axial, now it changes to equatorial. Due to flipping, C10 hydrogen is axial, now it changes to equatorial. So both axial hydrogen after flipping, it changes to equatorial. So always due to flipping, axial changes to equatorial, while equatorial changes to axial. But orientation never changes. You can see the orientation of this C9 hydrogen is up. Up means it is a beta oriented, but after the ring flipping, that hydrogen is still beta oriented. So facing in a top direction, it is still beta oriented. The orientation of C10 hydrogen is alpha. But after flipping, that hydrogen again, it remains as alpha only. So due to flipping, these are the observed changes, that is axial changes to equatorial and equatorial changes to axial. As the C9 hydrogen changed to equatorial, therefore the ring bond is now axial. So this bond is axial. Same thing, as the C10 hydrogen goes to equatorial, therefore C10 ring bond is again a axial. So this is a 1-2 fusion, that is the next ring start from number 9 and number 10. So we call this is a 1-2 fusion. And 1-2 fusion, you can see that this axial bond cannot make a ring with the axial bond of 9 number carbon. So you can see there is the ring formation is totally not possible because they are away from each other. Therefore, ring flipping is not allowed. As the ring flipping is not allowed, so you can see here only 1,2-EE fusion is allowed, while AA fusion is disallowed. So no AA fusion, no AA fusion. So trans-decalin not undergoing a flipping, therefore we call this system is a rigid system. So trans-decalin never undergo flipping. The reason behind is 1,2-AA fusion is disallowed. We cannot make a ring, that is ring A, by using a 1,2 axial bonds. Now cis-decalin. So in cis-decalin, the flipping is allowed, and due to flipping, that this one is equatorial axial structure, this is equatorial axial structure, but here this is axial equatorial structure. So we call it is a both the conformers exist, EA conformer and AE conformer, both these things exist. So you can see here 1,2-AE or 1,2-EA fusion is allowed. So cis-decalin system is a mobile system. Mobile means that EA changes to AE and again reverse it changes to EA. And both the structures are having the same energy, therefore these two structures are equally populated. Now the question arises how to draw the flip structure. So the way we discussed in previous structure, you do the flipping of ring B. So take down the ring number 7 carbon in the downward direction, while number 10 carbon in the top direction. So you can see here, after doing this, you number the carbon 7, 6, 5, 10, 9. Now 9 hydrogen, which is axial, now that axial hydrogen changes to equatorial. So this hydrogen is now equatorial. Number 10 hydrogen is equatorial, now it changes to axial. So number 10 hydrogen is axial. So the ring bond which are remained at number 10 and number 9 is axial bond and number 10 is equatorial bond. So this is the equatorial bond. So therefore this conformer is called as a AE conformer, and then you complete the ring, that is ring A. So cis-decalin system is a mobile system. EA changes to AE, or in other words 1,2-AE or 1,2-EA fusion is allowed. So for 1,2 fusion, there are three types of fusions allowed: 1,2-AE, 1,2-EA or 1,2-EE. 1,2-AA fusion is not allowed at all. So the same is written over here: 1,2-AE, 1,2-EE, and 1,2-EE fusions are allowed, while 1,2-AA fusion is not possible. The energy calculations. So let us start with the first of all trans-decalin system. In trans-decalin system, as there is no actual substituent, therefore there is no Butane-gauche interaction. One more thing, like cis 1,2 dimethyl cyclohexane, that time the 1,2-EE energy we always consider that time 1,2-EE. But in this case, we are not going to consider this as a 1,2-EE interaction. The reason behind it, these bonds are required for the ring formation. So same thing here with respect to ring B, these are the 1,2-EE interaction, but with respect to ring A, this 9,8 and 10,5 are the 1,2-EE interaction. So overall, there are two 1,2-EE interaction, but we never count these two interaction. The reason behind is that bonds we require for the ring formation. Therefore, here the 1,2-EE interactions are not considered. So in terms of Butane-gauche interaction, the number of Butane-gauche interactions are 0. So on energy of this molecule in terms of Butane-gauche interaction is 0 kilocalorie per mole. Or in other words, trans-decalin system is more stable. The reason behind it, the energy of this molecule is 0 kilocalorie per mole. Now let us calculate the energy for the cis-decalin system. Now in cis-decalin system, here is a little bit different scenario. The reason behind is one ring is vertical, so ring A is vertical while ring B is a horizontal. So with respect to ring B, first of all, horizontal, with respect to ring B, first of all, we are going to calculate the number of Butane-gauche interactions. So with respect to ring B, now this C10 C4 bond is axial. So with respect to ring B, so whatever the energy interaction, energy calculations are shown here that are with respect to ring B. So with respect to ring B, this bond is axial, that is C4 C10. So for axial bond, there are Butane-gauche interactions, two Butane-gauche interactions, that is four carbons, number 4, number 10, number 5, and number 6. So this is the first butane-gauche interaction, that is C4, C10, C5 and C6. So this is one butane-gauche interaction. Another butane-gauche interaction is C4, C10, C9, C8. So always remember, if we are going to calculate the Butane-gauche interaction with respect to ring B, so with respect to ring B, this is the axial bond. So for the axial bond, we have to find out the Butane-gauche interaction in the same ring. So total interactions here, C4, C10, C5, C6, C4, C10, C9, C8. So these are the two Butane-gauche interaction. Now what we have to do now, so with respect to ring B, there are two Butane-gauche interaction. Now to see how many interactions are there with respect to ring A, for that what I am going to do, so this ring I am changing the direction of this. Instead of vertical, now you can see the arrow direction. Now this ring, ring B, I am going pushing it in the downward direction so that automatically ring A is vertical, automatically ring A is horizontal. So you can see the same structure. I'm not flipping the structure, I'm just rotating the structure, that is the ring B I am converting into a downward direction and ring A in upward direction, that's why the ring A is horizontal and ring B is vertical. Now with respect to ring A, the C9 C8 bond is axial. With respect to ring A, now C9 C8 bond is axial. Therefore, again, there are two Butane-gauche interactions with respect to ring A. And which are those? That is C8, C9, C10, C4. This is one Butane-gauche interaction. And another Butane-gauche interaction is C8, C9, C1, and C2. These are the two Butane-gauche interactions with respect to ring A. So with respect to ring A, C8, C9, C10, C4, this is one interaction. C8, C9, C1, C2, this is another interaction. And you can see here that this interaction C4, C10, C9 and C8, and here also the same interaction we counted twice. So overall, though we see here 4 Butane-gauche interactions, but one interaction counted twice. Hence, instead of 4 Butane-gauche interaction, there are only 3 Butane-gauche interaction. So the calculations, 1 to AE, 1 to EE interactions are not considered as the bonds are used for ring formation. The same we discuss in trans-Decalin. The total Butane-gauche interactions are 3 instead of 4. So 3 into 0.9 is equal to 2.7 kilocalorie per mole. But this is the calculated energy for cis-Decalin. But the observed energy for cis-Decalin is 2.4 kilocalorie per mole. So every time, instead of taking 2.7 kilocalorie per mole, when we are going to talk about the 666 fusion, that time for energy calculation, the value that is 2.4 kilocalorie per mole, that value we are going to consider in case of a cis-decalin system. So observed value is 2.4 kilocalorie per mole. Now the optical activity, the trans-decalin system, the first thing, it is optically inactive. The reason behind is there is no chiral center, chirality is not there. Again, one more thing, you can see there is a C2 axis of symmetry. So passing this axis, there is a C2 axis of symmetry. You can rotate this, then 7 is here. So you can see there are C2, that is two-fold axis of symmetry. At the same time, there is a center of symmetry lying at the mid of the C9-C10 bond. So at the mid of the C9-C10 bond, there is a center of symmetry. So the one thing it is first, the important is there is no chiral center, therefore it has to be optically inactive. But at the same time, there is a C2 axis of symmetry as well as center of symmetry lying at the mid of C9-C10 bond. Therefore, transdecalin is optically inactive. In case of a cis-decalin system, actually there is absence of chiral center. So we expect that cis-decalin system, because of there is no chiral center, therefore it has to be optically inactive. But the observation is that the conformational analysis of cis-decalin shows that it is a chiral molecule, though it has no chiral carbon. Because of that, it has non-superimposable mirror images. As it is having a chiral center, therefore it has a non-superimposable mirror images. But due to rapid ring flipping that we already discussed in ring flipping, that AE structure and EA structure both are equally stable. Therefore, the ring flipping is rapid. Because of that, it cancels its chirality and convert it into its mirror image. Thus, two chiral forms are non-resolvable, like a cis-1,2-dimethyl cyclohexane, though there is absence of symmetry, but still cis-1,2-dimethyl cyclohexane is optically inactive. The reason behind that these two forms are non-resolvable, that is due to ring flipping, that it gives a mirror image. So flip structures and mirror images are the same. Because of that, cis-decalin is optically inactive. So for this, you refer these books, Ilil, Nasipuri and Kalsi.